Greetings learners, and welcome to our third lesson in Unit 3 on phases of matter. Today we're going to be learning about gases and pressure and the relation between the two. And we're going to learn about the kinetic molecular theory, and after today's lesson you should be able to describe gas behavior using the points of the kinetic molecular theory. So to start, what is the kinetic molecular theory? Well, it describes ideal gas behavior, which is exactly what it sounds like. It's ideal behavior of gases. It doesn't mean that it's necessarily how gases actually behave, but it's a theory that we use to describe in a perfect world and give us a model of theory, a little bit better of an understanding of how gases are going to behave under different situations, different circumstances. So the first part of this theory basically says that gas particles, gas molecules, are tiny and very far apart from each other. So the distances that separate them are much greater compared to their size. And generally, if we think of this as a particle diagram, if we see gas inside of a closed container, we're going to see particles that are very far apart from each other and very small. And in general, we'll only see a couple different atoms or molecules in the particle diagram, and we want to make sure that we show them towards the edges of the container. We don't want them to be close from each other because the KMT, or the kinetic molecular theory, says that their distances between them are very large. The second part says that gas particles move in a straight line. So when this guy's in motion, he's going to move to here, this one to here, and if they happen to run into each other, they're going to bounce off of each other and move in another straight line in another direction. We're assuming that, and again, this is what makes it ideal and not real gas behavior, that gases aren't moving in any type of curved path. And that just helps us to describe their behavior and make predictions. We assume that collisions between gas particles are what we call elastic. And in an elastic collision, we assume that there's no energy lost. So all the energy from one particle gets transferred elastically without any loss of energy to the other particle. So for example, if we were to have, let's say, one particle sitting here, not moving, and another one coming at it, I'm going to use this with this, let's go with a speed. That's probably most relatable. Let's say a particle or a car. We'll do this with cars. A car is moving at 10 miles per hour. You consider it as a particle as well. And it hits a car or a particle that's not moving. It's sitting there at 0 miles per hour. The elastic collision means that when this 10 mile per hour particle or car hits the one at 0, and let's say they bounce off of each other, this one might be moving at 5 miles per hour and this one's moving at 5 miles per hour. Or we could have a complete transfer where maybe now this one's moving at 10 miles an hour and the one that was traveling at 10 is now not moving at all. We actually wouldn't see this arrow here if it's not moving. So we assume that there's no energy lost really to the container or the surroundings that the gas is in. The next part is that we assume that gas particles have no IMFs, no intermolecular forces, meaning that the force of attraction between two particles is non-existent. And that's because they are such high energy. Do they really have some small force of attraction to each other? Yeah, or repulsion. But under this theory, we assume that they don't, and it helps us to describe their behavior, again, in an ideal environment. The fifth part is that the hotter the gas is, the faster the gas particles move. Now we know that when we're talking about how hot something is, we're referring to temperature. We know that temperature is a measure of average kinetic energy. So if the temperature goes up, the average kinetic energy goes up, and if you have more kinetic energy, then you are moving faster. So as we heat up particles of gas, they're going to start moving faster. Once we apply energy to a gas, that energy has to go somewhere, and it's going to be absorbed or transferred into the motion of the gas. Now we know that no gas is truly ideal. As we said, it's describing ideal behavior, but it is not actually a real gas. Those are two different things. So no gas actually behaves ideally, but there's two conditions that will allow it to behave most ideally. And this is under conditions of high temperature and low pressure. So we have high temperature and a low pressure. If we have these conditions, whatever gas is inside will behave most ideally. And if we reverse those to low temperature and high pressure, then they would be least ideal. The next part is that the smaller the molecule is, the more it will behave. So the smaller size molecules, let's say something like H2 gas, we do a little simple particle diagram here, compared to Cl2 gas, the smaller the gas molecule is, the more ideal it's going to behave. The larger it is, the less ideal it's going to behave. So gases like hydrogen and helium are going to behave most ideally because those are our two smallest gases. Now this gentleman here with his picture up in the corner, his name was Avogadro, and he had a hypothesis. And among many things that he did to the chemical community, he came up with this idea that if we have equal volumes of two different gases, and we make sure that they both are at the same temperature and are exposed to the same type of pressure, then inside those two separate containers we're going to have the same number, an actual same number of molecules. And because, since atoms are so small, because we're going to have such a large number, he decided not to use the actual number that he thought would be contained for a number of particles for that gas. And he decided to use a quantity that we call the mole. And a mole of particles is equal to 6.23 times 10, excuse me, 6.02, I'm getting my numbers mixed up here, 6.02 times 10 to the 23rd. So if we think of that, a container that's holding 22.4 liters, so a volume of a container that can hold 22.4 liters of a gas. If we have two containers there, same size, 22.4 liters, same pressure, same temperature, they're going to contain the same number of particles, and that's going to be 1 mole. And this gives us a way to compare different types and quantities and volumes of gases. So the math that we do with one gas can be applied to any gas. So in the example on the bottom here, we have 3 different gases all containing different numbers of atoms, 2, 4, 3, with different elements at different weights. But if all the gases are at 298 Kelvin, and what we'll learn here in a second is standard pressure, then each of those containers is going to contain equal numbers of molecules. And that number is what we call 1 mole, which is kind of similar to a dozen, where a dozen describes 12 and 1 mole describes 6.02 times 10 to the 23rd, which is a really large number. So we use scientific notation and even further an abbreviation to represent that number, which allows us to do some more simplified math. Now there are deviations from ideal gas, because we're not always going to have the same conditions of what we call STP. STP stands for standard temperature and pressure. And we can find those conditions on table A on your reference table. This is going to tell us what the standard pressure is at sea level and what our standard temperature is, which you might kind of think is kind of cold, but in the form of matter at 273 Kelvin, remember it can still decrease by 273 Kelvin down to absolute zero or 0 Kelvin. If we remove the conditions of standard temperature and pressure, we are no longer talking about ideal gases. Ideal gases have to be considered under conditions of standard temperature and pressure. Let's do a little practice. Feel free to pause the video, try the question, and check your work. In which way do real gases deviate from ideal gas behavior? Well, we want to think about what is ideal gas behavior, and that's described by the kinetic molecular theory in those 5 parts. Now, the first part had said that gas molecules are extremely far apart from each other compared to their size. So this would be true. It's not a deviation from real gases. Real gas molecules have attractive forces. Well, the KMT said that ideal gases don't have attractive forces. So we'll come back to that one. Real gas molecules move faster at higher temperatures. The KMT did say that as we increase the average kinetic energy of a sample, the molecules, or atoms, are going to absorb that extra energy and start moving faster. Real gas molecules travel in a straight line. This is also mentioned in the KMT, that gas molecules, when they come in contact with the walls of their container or another gas molecule, will bounce off and move in a straight line in some other direction. So this choice here, B, real gas molecules have attractive forces, this is true. You're going to have attractive or repulsive forces, whether they're extremely large or extremely small, it doesn't matter. They're still there. And the ideal gas behavior says that gas molecules do not have attractive forces, when in reality a real gas molecule will have a attractive or repulsive force, even if it is extremely small. Practice question number 2. Which sample of gas contains the same number of molecules as a 2-liter sample of oxygen gas at 300 Kelvin and 100 kPa? Now, the first thing we want to look at when we're comparing gases here, and we're looking to see which sample of gas contains the same number of molecules, well, Avogadro said if we have different gases at the same temperature and pressure, and they're going to contain the same number of molecules. And we also have to match the volume, and we find that by the unit with the symbol of liter, capital L. So we have a 2-liter sample of gas at 300 Kelvin and 100 kPa. So we'd want to find these matching conditions, and if a different sample of gas is present at those same conditions, then it should have the same number of molecules as the sample in the question here. So we're looking for one that has 2 liters, so we can rule out A, and we're looking for a temperature of 300 Kelvin. Both B and D have a temperature of 300 Kelvin. C does not. 350 is higher than 300. And 100 kPa, that pressure is going to match up with D. So these conditions match. So therefore, the chlorine gas and the oxygen gas, under the same conditions, should have the same number of particles in their sample. Now, a little bit about pressure. Pressure is defined as force exerted over an area, and we have actually a fair amount of pressure on Earth, and that's a result of the gases in the atmosphere overhead that are pushing down on Earth and consequently you and I. And if you think about this, well, how could atmosphere, gases in the atmosphere, be heavy enough to cause pressure? Well, if you think of you standing underneath a piece of paper, or you put a piece of paper on your head, you might not even notice that it's there. And you can think of this, I guess we'll stick with paper. I don't want to go too far with this. You might not notice one single piece of paper on your head, but if you start to stack paper over paper over paper, and you get to a ream of paper, then you're definitely going to notice that, and that's causing a force downwards on your head due to the force of gravity, which is the same reason why we have gas molecules that are staying in our atmosphere towards Earth. They're being pulled down towards Earth. So all this atmosphere, 600 miles worth of atmosphere, and all the gases that are contained in it are pushing down on us, and that causes pressure. And at sea level, the pressure that's exerted is around 14.7 pounds for every square inch. And that's being applied on every square inch of your body. And that's a fair amount of pressure. And that's what's responsible for a lot of the behavior of matter, particularly gases, that we experience here on Earth. And that's what changes from world to world, and why life, as we know it, is partially not possible because of the lack of atmosphere and pressure. And we can feel the change in pressure on Earth as we go up or down a mountain. It could be as simple as the pressure changing in your ears, and you can feel that where you might have more pressure inside your ears pushing out as you go up a hill or up a mountain. If you are traveling up a larger change in elevation, you can really feel that. And one of the ways that you can feel it is due to your ability to breathe. The farther up we go, away from the surface of sea level, we have less and less gas moving around at that point. Let's say halfway to here, now we only have 300 miles of atmosphere sitting above us, and it's 300 miles of thinner atmosphere. Less gas weighing down on you, less pressure, less available oxygen, makes it harder to breathe and catch your breath. And this atmosphere is what's actually responsible for keeping all of your liquids in your body in the liquid phase. If you were to go into outer space, remove yourself from a space station or a space suit, you would be exposed to near zero pressure, and there's nothing actually keeping the liquids in your body in the liquid phase. And we're going to talk about that in a moment here. So we don't have pressure, so the vapor pressure is great enough, which we'll learn about in a second, to cause the liquid to evaporate or boil immediately. So the gases or the liquids that would make up your body are then boiled or turned into a gas and are able to leave your body, which your body's not meant to have gaseous blood in it, so you would not survive that type of change. So something as simple as pressure from invisible gases in our atmosphere is what's keeping our bodies functioning the way that they're designed to. Now sometimes you're going to have to be able to convert between different pressure units, and luckily in the scope of this course it's only two different units, and those units are kilopascals and atmospheres. So we need to be able to convert between them using dimensional analysis or the ratio method. And we'll do a couple examples here. Remember, we can find standard temperature and pressure values on table A on page 1 of our reference tables. Standard pressure being 1 atmosphere or 101.3 kilopascals. So those are the two values we will use as our conversion factors to convert between the two. So when we convert 2.35 atmospheres to kPa, we know that there's 101.3 kPa per 1 atmosphere. Atmospheres cancel, we end up with 238 kPa. For the opposite, going from kPa to atmospheres, we are going to divide by 101.3. So if we want to convert 1.234 kPa, we have 1 atmosphere for every 101.3 kPa. This allows kPa to cancel. We'll be left with atmospheres, and we get 1.218 atmospheres. Well, that should be 123.4. Decimals in the wrong spot. Wait a minute, 1.234 divided by 101.3 is not 1.218. So that's a mistake on my part. That should be 123.4 kPa. I'll give you a second to practice the questions on here. Feel free to pause the video and attempt the practice problems. So to do this one, 3.2 atmospheres, we know that there's 101.3 kPa in every 1 atmosphere. So we're multiplying those two together, and we get 324.16 kPa. Now to go the other direction, we're going to divide 232.9 kPa. We're going to divide that by 101.3, or if you're using dimensional analysis, we will still multiply. kPa cancels. We're left with 232.9 divided by 101.3, and that gives us an answer of 2.3 atmospheres. And we could actually expand on that, as we start with 4 sig figs here. This should be rounded to 4, so we're going to call that 2.299 atmospheres. Remember, we want to keep the same number of sig figs as what we are converting from. This 324.16 would round to 320 kPa to keep in line with the 2 sig figs from our original number. And the last thing we're going to talk about for today is vapor pressure, which is defined as pressure exerted by a liquid's vapor in a sealed container at the vapor-liquid equilibrium at a given temperature. And this is going to change with temperature. Given and I always think of this as a container of gasoline that's sitting in the sun. If you've noticed this, if you leave a can of gasoline in the sun and you go to open the spout on the top, you're going to hear kind of a pop when you open it. And that's the gas that's been building up in there as it sits in the sun. And once you open the top there, you relieve some of that pressure. But if you put this gas can in the middle of outside in the middle of winter, even if it is in the middle of the sun, we're probably not going to have much vapor buildup in here at the lower temperature. But as the liquid inside converts to a gas, and in a sealed container, we'll learn about this with equilibrium, those two phases can exist together, and the gas is going to exert some pressure on the inside of the container. Now, the stronger the attractive forces between liquid molecules, stronger the IMF between them, the lower the vapor pressure. Which means it's harder for these, the force is stronger between the molecules, it's going to be harder to break them apart. And if we want these to be a gas, they need to break their bond from each other and move in different directions. Now, substances that have a high vapor pressure are volatile and evaporate quickly. Things like acetone or alcohol, if you leave them out on the counter, given a short amount of time, because of their high vapor pressure and low intermolecular forces, they're going to evaporate quickly, which makes them volatile because these substances, acetone and alcohol, as a vapor or gasoline, are very flammable. Now, a boiling point is defined as the temperature at which a liquid's vapor pressure equals the pressure exerted on the liquid by outside forces. So if we think of a container of water, the liquid that's in here, we're going to have some of that liquid converting to a vapor on the surface, and those molecules, as they escape the liquid, are going to cause some pressure. Pressure being caused by collisions on the walls of a container or on other gas molecules. So when that vapor pressure equals the pressure coming down on it from the atmosphere, then the liquid is able to boil. And oftentimes, in order to get this vapor to be stronger than the atmosphere, we need to give it a lot of energy and heat it. But boiling doesn't mean that you have to heat it. All that it means is that this vapor pressure coming off the liquid has to be equal to or greater than the force weighing down on it. So if we were to remove the force of the atmosphere, then the liquid is free to change to a vapor and escape the container with very little energy. And this is what happens if you were to step out into outer space with no protection. We no longer have atmosphere pushing down on the liquids in our body. They're free to evaporate into a vapor, into a gas, and free to move out. So we can get a substance to boil at a lower temperature if we lessen the force of the atmosphere on top of it. And this is why at higher elevations, water boils at a lower temperature. So if we were to go somewhere like Denver, which is 6,000 feet or so above the surface of sea level, water might boil at maybe 180 degrees Fahrenheit as opposed to 212 degrees Fahrenheit. Or maybe at something like 90 degrees Celsius instead of 100 degrees Celsius. And actually at school here, we're not at sea level, and water doesn't boil at 100 degrees Celsius. It boils somewhere around 98 degrees Celsius, because we experience less than 1 atmosphere of pressure at school here. Now we're going to use Table H to learn a little bit more about vapor pressure. Now on this table, you have 4 different curves, and the curve represents the boiling point for each of those 4 substances at a particular temperature and pressure. And you can see that this curve changes as temperature increases. Now this dotted line that runs across here is our normal boiling point. And this is atmospheric pressure, standard pressure. So at standard pressure, when that curve crosses that standard pressure line, this is our boiling point. And that's going to change depending on the pressure of the atmosphere. But the normal boiling point refers to where these curves cross that dotted line. Now you'll see 3 different types of questions when it comes to vapor pressure and using this table. And it might be something like, what is the vapor pressure of ethanol at, I don't know, 75 degrees Celsius. So we'd say, okay, we want the vapor pressure of ethanol. Here's ethanol, 75 degrees Celsius. It crosses the line right here. What is the vapor pressure at that point? And that would be something like, I don't know, 85 kPa. The other type that you might see is, what is the boiling point of, let's say, water at a pressure of, let's say, 50 kPa. So we find water in 50 kPa, and we drag it over to our line here, and then we trace it down. So at a pressure of 50 kPa, water is going to boil at somewhere around 84 degrees Celsius. So we can either determine the pressure at a particular temperature, or we can determine the temperature at a particular pressure. The third way that we'll see questions is if you're asked what's the normal boiling point of, let's say, propanol. And the normal boiling point has to do with where the propanone line crosses our standard temperature, our normal pressure. And the boiling point refers to a temperature, not a pressure. So we trace this down, and we're looking at something about maybe 56 degrees Celsius. Now with these two different curves here, we can see that the stronger forces are going to boil at a higher temperature. So stronger forces in ethanoic acid and water attribute to their higher boiling point, and propanone and ethanol would have weaker forces, which cause their boiling points, their normal boiling points, to be lower than water and ethanoic acid, which have stronger attractive forces between their molecules. If you guys have any questions on any of this, make sure you write them down and bring them to me so we can discuss them. Hope everyone has a great day.